Okay, I think we're going to go ahead and get started. So because we want to start things off extra exciting, we have two projectors on at the same time, which will increase the wow factor quite a bit. So I'm Daniel Whitenack. I'm a data scientist and developer advocate with a company called PACHYDERM, which has an open source project of the same name called PACHYDERM. If you're coming in, grab one of those stickers or cards as you come in. You'll need one of those. It has an IP address on it. So I'm really excited to be here. I want to thank the organizers for giving me the opportunity to give this workshop. This is my first official Julia event. So I'm pretty excited to be here and learn from all of you brilliant people here. But today, to kind of kick things off in this first workshop, what we're going to talk about is integrating Julia into real-world distributed pipelines. So that's kind of a mouthful. But basically, what I mean by that is I'm not really going to go through a whole bunch of details about like specific techniques in coding and programming Julia. But the premise is basically that we have developed some programs, some Julia programs, some applications that we want to actually start producing value within our research team, within our company. And in order to do that, we actually need to get them off of our laptop, right? And not only that, pretty much all of the data analysis sorts of problems that we're solving are multi-stage problems. So we might have to do some pre-processing, we might have to do some visualization, and all of these different steps. And so these are kind of by their very nature multi-stage workflows. And when we start talking about getting those off of our laptop, we need to start thinking about how we're going to connect these things, how they're going to communicate, how we're going to manage those things. So that's really the premise of this workshop. Are there questions about that before we kind of dive in? And feel free to interrupt me with questions too. Okay, cool. So the flow that we're gonna execute here is as follows. First, we're just going to talk a little bit about what some of the challenges are with performing this sort of integration of Julia into a production environment, into a distributed workflow. And then we're going to go on and talk a little bit about Docker, because that's going to play a pretty important piece in at least the solution that I'm going to show you today. Then we're going to actually the hope is to all kind of deploy a multi-stage workflow on a cluster today. So each of you should have got an IP. That IP is connected to a cluster. And the hope is that each of us are going to actually deploy a workflow, Julia-based workflow, to a cluster, multi-stage, in a distributed environment. So sound fun? Okay. Awesome. Sweet. And then I'll give you some resources at the end that you can follow up with. But all right, let's go ahead and start talking about some of the challenges here. And kind of out of those challenges, some of the goals that we want to kind of guide us as we develop this solution. So the first challenge that I would propose as a challenge in taking what we are producing on our laptop and actually integrating it into a team's infrastructure, into deployment, is around reproducibility. And I already see some of you guys snickering. This was like my graduate work. Like what happens over time is like you kind of start out pretty simple, and then you develop a bunch of different stages of your processing and a bunch of different collections of data. And then eventually you get into this scenario where you have like all of these different things, and you have no idea how things fit together. And moreover, if you even hand things off to another person, it's even harder for them to kind of deduce what you've done. And you end up with these really long names, like generating good figures this time with my second config, .ipymb or something. So I think probably all of you guys are familiar with this, and we really should care about reproducibility. I probably don't need to talk about that too much in this context, but really it's something that we should be striving for, even though it's not always realized. The second challenge is around kind of generally what I put as audit trails and debugging and maintenance. I'm going to talk about this in terms of provenance later, this word provenance. But basically the idea is that, again, not only are we trying to reproduce a specific thing that we've done, but oftentimes we have this whole workflow that we're working with, whether that's a bioinformatics workflow, or whether it's a machine learning workflow, or just like we're transforming database tables, or whatever it is. These often involve multiple steps, and so to go back at some point and try to understand like what came from where and contributed to what, and actually debug that, track it so that we can revert when things break and all of those things is rather difficult. Not to mention that, again, like on our laptop, it might be kind of easy to string these different steps together, but as we get it off of our laptop, we have to question and say like, okay, how am I going to input the output from my pre-processing into my model training, et cetera, down the line. The third challenge that I'll mention is around kind of general workflow management, which I think is very relevant in this audience. So this is a picture from Josh Wills. He's director of data platform at Slack, or at least was the last time I checked. But basically the idea is that like we all have things that we like to use, tooling and frameworks that we like to use, Julia being one of them. And oftentimes when we're thinking about integrating our applications and our workflows into the general like picture of what's going on at a company, or what's going on in a research group, or what's going on at an institution or organization, a lot of other people aren't going to be familiar with those tools and frameworks, and they might not be integrated very well with the way that certain things are deployed in certain environments and that sort of thing. So this creates a lot of friction with people like data engineers who have these really awesome data pipelines, and they're like streaming things really fast, but then like we can't necessarily always figure out how to integrate our stuff with that stuff. And if we can't get it off of our laptop, obviously that produces friction with an actual organization, because at the end of the day, you're getting paid to produce value within a company, or you're personally trying to accomplish some research project, or get to certain results. So this kind of creates friction all around. Yeah, so those are kind of my three areas. Are there any like comments, questions, thoughts about that? Maybe I shouldn't ask for thoughts, because there might be a lot of thoughts about that, but no? Okay. So I promise we're getting to the hands-on stuff soon. I just want to lay out some initial goals that we're going to try to accomplish in this process. So based on those challenges that we just saw, the first goal that we're going to have is around reproducibility. And this basically means in this context that for any stage of our processing, we should be able to input the same input data into that stage, and at least produce results that occur also within the expected set of results for that stage. So sometimes that means you put in the same data and you get out the same number. That's not always the case if you're dealing with randomness and other things. But we should at least have a grip on how we can reproduce things within an expected range of behavior. Second, I'm going to talk about provenance, and what I really mean here is that we have a bunch of Julia programs, and we're doing pre-processing and visualization and whatever it is. We should be able to kind of have a strict tracking of this piece of data over here that I produced was a result of these stages of processing along with these particular states of my data, such that we have a very, very clear lineage of what data contributed to what other data and what processing we did on it. And this will be a huge help in terms of both incrementally improving on what you've been doing, but also in terms of compliance and in terms of debugging and maintenance and all of these things that we talked about. Yeah?
With that, are you thinking of it in terms of what people do with metadata? It's over here, but it's about the data, or something that's integrated with the information as you...
Yeah. So the question was if I'm talking here about like representing this provenance with some sort of metadata about what's going on, or if it's somehow like tighter coupled to the actual data that's being processed. In the example that I'll show, it would be kind of the latter, more tightly coupled to the actual data that's flowing through through the pipeline. But there's various techniques out there, some which only use metadata to represent what you've done. I think the key thing though is with that sort of approach is that if you have information about what you did, but you still don't have the exact state of that data, then you really can't reproduce what you've done. You might be able to gain some insights about it. I'm not saying that, but it doesn't really get you back to any sort of that state or yeah. So I think that's the differentiator that I see. But there's certainly use cases for both. Other questions? All right. So the third thing I'll talk about is autonomy. I mean autonomy here for us, the people that are developing these analyses, because again, we all love Julia, and so we want to use what we like. And maybe you have a bunch of other things that are maybe even specific to your use case, like bioinformatics things or computational physics things or certain machine learning frameworks, and you want to be able to utilize the things that you need and want to use. And so we want to preserve that. We don't want to get away with that and just say, well, like all big data stuff is written in Java Scala, so let's all switch to Java Scala, which probably wouldn't go over well here. Okay. The last thing that kind of builds on that and complements that is compatibility. So yes, we want to be able to use the tooling that we like, and we want to be able to use Julia and these other things, but we can't just like have the excuse that we're going to use the things we want and all of you deal with it. We should have some strategy in place to where, yes, we're going to use the things that we want to use, but we should have sympathy and empathy for those that we're working with and be able to integrate into a wider range of tooling. So those are my goals. Anyone else have any other goals, questions, snide remarks? Anything? Yeah.
Just on that last one, just a remark. Sometimes you don't have a choice as well. Like you have all this code, which is lazy code, or you have some Python tools, which you just instrument produces some data in this format. You can't deal with it unless you have their tool.
Right.
So it's great.
Yeah. So the comment was that sometimes really like even if you have preferences, you're not always able to execute on those because of certain formats that are forced upon you or certain constraints. And yeah, I think that's exactly right. Sometimes like you have to be compatible just for those reasons. And you have to have that flexibility. You don't want to be like tied into any one particular thing too much because then you won't have the flexibility to deal with those scenarios. Yeah. Yes. Yeah, so the comment was that in also there's often a resource constraint that's relevant here because like, if you really love Spark, right? And you do this one single thing in Spark, and so you always want to have a 15 node Spark cluster up to do that one thing, that has very real implications on like the resource usage just for that one thing that you're doing. So you also want to, I think, have flexibility. So yes, have flexibility in the tooling, but also have the flexibility to spin up the things that you need when you need them and be able to also scale down when you don't need them. So yeah, that's a good point. Other thoughts? Okay. So in thinking about these goals, and in particularly the goals around autonomy and reproducibility, one thing that we automatically run into when we're developing applications on our laptop and we have like the Julia code we like or whatever code that is, and we're thinking about pushing it off of our laptop, the first thing that kind of comes to mind is that you're going to be executing this in an environment that you didn't develop it in, right? So you have your nice setup on your laptop, everything's cool, you have the specific versions of whatever and whatever, and it works fine. But in moving that off of your laptop, you're kind of going into the Wild West. You have to be able to have, again, if we're thinking about reproducibility, you have to be able to have some confidence that your application is going to exhibit similar behavior as you move it off your laptop into a potentially very different environment. So that's where I'm going to bring up Docker, and we're going to use Docker today in our workshop. So how many have heard of Docker? Okay, pretty much everybody. How many people use Docker? Okay, actually, yeah, quite a few. So we can smoke through this part, but basically Docker is wildly popular. I say it's blown up, especially over the past few years, and the reason is kind of in the architecture behind Docker. So a lot of you are probably also familiar with virtual machines. So just not to bore the people that are familiar with Docker, but Docker containers or images are not like a virtual machine. One of the reasons why they kind of gain so much popularity is that, like with a virtual machine, you kind of have to have this guest OS in the virtual machine. You have to often specify what resources that virtual machine is going to take up. With a Docker image, basically each running container, which is a running instance of an image, so that's kind of the jargon, all runs on the same Docker engine and all shares the same underlying resources on your Linux kernel. And there's actually no OS in there. So that makes it both smaller, which makes it much more portable, but it also means that you can have a bunch of these Docker images running and they all share resources on your node. And anywhere that you have Docker running, you can pass around these very, very portable small containers and spin them up very, very quickly because they are small, because they're portable, and be able to pass them around into different environments where you can, again, have confidence that, like, if you run it on your laptop in Docker and you push that image to another place and you run it on Docker, it's going to run the exact same way, assuming you put in the same data and all of that. So are there any questions about that? Okay. So again, just to reiterate, this kind of gets to these different goals that we're talking about around predictable behavior of Dockerizing our Julia application and then it having similar behavior in the environment that we're running it in. And then also, we can put anything in a Docker container. We can run a bash script, we can run Spark, we can run a database, we can run Julia. So it also gives us that element of autonomy. And also, I don't know, I might be a little bit bold saying that it's some type of industry standard here, but I think it definitely is widely used across industry and now even in academia. And I think it's something that's going to be sticking around and something that is going to be used by a lot of different teams and contexts. So let's go ahead and look a little bit at this. So switching context a little bit, are all you guys, so before we get started, did all of you get one of these stickers or cards with an IP address on them? If you didn't, I think, are they all out? There's one more. There's one more. So, okay, so there's two more here. Grab one if you don't have one. And if we run out, pair up with one of your nice Julia friends. And you can look on. But so that IP address is kind of your dev workshop instance for this workshop. The other thing that you'll need is, if we look here, so everyone can go to this, so go ahead and pull up this repo and just, you can pull this up and just keep it up throughout, because all of the commands that we're going to be executing and that sort of thing are contained in the README here. So if you get lost or you don't remember what I typed or I moved on, you can always look back to this README and see what we did. And we'll also clone this on the machine. Oops. Okay. So those are kind of the prereqs there. The other thing, we'll want to pull up a terminal window. And you can then, let's see, I think.
You press enter or something, bring it down.
Oh, I'm sorry. Yeah, let me, thanks. There we go. Okay. All right, so once you have that IP, we're all going to log into our machine. You can utilize the user pachrat, like shown here, PACHRAT. Okay. That's going to ask you for a password, and the password is PACH, password, all lowercase. So again, password, PACH, password, all lowercase. Okay. And feel free, so I probably, throughout the whole thing, I won't be able to run around and get everybody's questions, but you know, we're a great community and we work well together, so feel free to get help from your neighbor as well as try to answer as many questions as I can. But are most people kind of able to log in there? Yep. All right, cool. Password, PACH, password, all lowercase. So I should mention too, if you do miss any part of this, in the repo, so over here, if you look, all of this is spelled out, you know, throughout the repo, and if you go down here to the resources, there's a link to spin up PACHYDERM locally. So even afterwards, if you miss something, if you want to run through it again, it's really quick to spin this up locally, and you can go back and do that. And I'll be around for the next few days. So again, if you miss anything, we can just sit down at a coffee break and go through it. So don't worry too much about that. But the thing I wanted to show you basically is that, so let's first clone this repo. So you can go over here, grab the URL, and here on the box, just do git clone with that URL. And that should give you this directory, Julia Workshop. Let's go ahead and go in there. You'll notice a few things that we'll be using through here. But just to illustrate this, this Dockerized Julia thing, let's go into this train-tree directory. And I just kind of want to show you this, and then I'll kind of demonstrate how a few things work with Docker. We're mostly going to utilize this Docker instance, but I did want to show you, or image, but I did want to show you a few things. So the first thing you'll notice here is I have this Julia program. It just uses decision tree to train a model, and we'll talk about that more here in a second. And it saves the model out to a JLD file, a local file. Okay, so I guess what I wanted to show there's nothing too interesting. I just wanted to show I'm not importing anything special. I'm not like using PACHYDERM or something like that. This is just kind of what you, kind of a standard Julia program. The other thing that's in here is this program that will install our various dependencies. And in order to put this all into one of these Docker images that we can make portable and move around and all of that, what we need is a Docker file. So you'll also see that there's a Docker file in this directory. And let's just go through that here really quickly, because this might be the thing that's new to some of you guys. So the way that a Docker file works is basically you can imagine that you're on your laptop or whatever, and you're installing some new stuff, and you just want to make sure you have everything you need to run the program that you're interested in running. Okay? So here you can see in the middle, I'm installing some things. I'm running that package installs to get my installs. I'm doing a little bit of cleanup. So these are just similar things that you would run on your laptop. You just give it a Docker keyword. So you're saying run this, or add this to my Docker image, or set this environmental variable, etc. Okay? And then at the end, all I'm doing is I'm adding that Julia program that I just showed you to my Docker image. Okay, so everything's built up just kind of the way that you would build it up on your laptop. And then at the top, you can see I'm saying from Julia. So what this means is that there is already a public Docker image that has the basics to run Julia. So if you get that image, you can spin it up and you can run Julia. It just might not have all the dependencies that you need for your specific thing. So we're starting at that base level, so we don't have to install Julia. We're just installing the things that we need and then adding our train.jl. Does that kind of make sense? How that works? Yeah.
So in Julia, if you need specific packages, where would you put that?
So that I included in this package installs here, which was a separate file here. And this structure I kind of stole from someone, but you basically list them out and add them. And then if you notice in my Docker file, here under the run command, I'm using Julia to run that script to install the packages. Other questions? Yeah.
Which version of Julia do that?
I think the latest, so if we look at, if you go here, you can actually track that. If you go to Docker Hub Julia, what now? 0.6, yeah. So you can see if you go to Docker Hub, which is where this is hosted, and then you look here, if you ever want to know like what is what, you can look here and then see that there are various tags and when those were updated, and also like yeah 5.2.
In the version now?
So I mean, it depends. Like this is totally up to you and how you run your what you need for your code. So this is what worked for me to just use latest and use that. If you had a specific need, you could specify that. Like if you go here, you can specify a specific tag like 0 point whatever with the colon is how you would specify that. But here we're just kind of using the default, which will be updated as well over time. Other questions? Yeah.
Some of us can't seem to log on.
Oh, okay. So are you getting an error or getting
Permission denied.
permission? Let me see.
You don't have PACHYDERM app. You need the username from the SSH.
Oh, yeah. So you need SSH, and the user is pachrat, P-A-C-H-R-A-T, at the IP address, and that's shown in the README too. So if you're wondering about that user, it's just that P-A-C-H-R-A-T, and then the password should work. Yeah, good. All right, cool. Anyone else having issues? What now? The what?
The build. Come on.
Oh yeah. So you won't be able to run the Docker build under this machine just for various permissions reasons. And also we shouldn't all do that. So if you have Docker installed locally, don't build the image during the workshop. I already have built it because we don't want to destroy the Wi-Fi. Okay. So I've already built it. I just wanted to show you kind of what those pieces are. And then here I can show you, I have this locally. So I've already built this image. And I'll just show you. So I have previously built the image. The build command is in the README if you're interested in it. You just have to do docker build blah, blah, blah. So now if you run it, here is train, Julia train. And I'm going to just bash into this container to show you what it looks like. So this is, I'm now inside of this running container. What I basically wanted to show you here is that, Julia is here with nice wrapping. And then also we have this script that I just showed you. So it's the same one in the Docker image. So we have Julia, we have our train.jl, and it includes those packages that we installed. Okay. So I know you can go back and run the Docker build and everything later, or I can help you like throughout the week. I just didn't want to like crash the Wi-Fi if we all did that at once. Sound good? All right. Other questions before we kind of move on? So this is kind of, I have this, we've built this Docker image. It includes the packages that we need. It includes our script. And if I run, so here I was running that Docker image on my local machine, and I can see how it behaves. We're going to use the exact same Docker image in our pipeline. And so we can expect that if that Docker image is running on Docker, which it will be behaving the same way as if it was on our laptop. Okay? Questions? Yeah.
Can you show your package install script real quick?
Yeah, sure.
Secondly, is there a reason you're not using like a command for your Docker file? You kind of just like
There is a reason for that. I'll get into that. Yep.
Okay.
Yeah, so here I kind of, maybe there's a better structure, I don't know. Oh, I should mention too, I'm expecting at least like 1 or 2 pull requests from you guys. I'll be disappointed if I don't get them, because I'm sure at least there's typos and maybe an error somewhere. So, or feel free to just improve my programs, because I want to learn from you guys too. But yeah, this is the package installs that I did, and what he mentioned, the question was, why is there not a command at the end? One way you can build a Docker file is to put a command at the end. So I could say like Julia train.jl with the arguments. And when I spun up that container, it would automatically run that Julia program. There is a reason why I didn't do that, which I'll get into here in a second, but that's another thing you can do with Docker for sure. Like if you're also spinning up like a web server or a database or something like that, that's oftentimes useful because you can just go ahead and spin it up and have it up. Other questions? All right, cool. How's everybody feeling? Good? Thumbs up? Kind of middle? All right, okay. All right. Let's go back here. So we've now talked about Docker and Julia and shown kind of how to build a Docker image, although we didn't all do it, but I promise you guys will be doing stuff here in a second. And we've kind of illustrated the idea that we can package up our application and run it with expected behavior in another environment, as long as that environment is running Docker. But we haven't really addressed some of these other things that we talked about initially. We haven't addressed this multi-stage sort of thing. We haven't addressed provenance. We haven't addressed like stringing things together. So now what I want to do is really get into the meat of what we'll be doing, this multi-stage distributed deployment that we're doing. And we're going to be utilizing these extra pieces. So we're kind of bolting this thing together as we go. But I'll explain those in a second. First, I want to just describe like the use case that we'll be solving and how some of these challenges pop up in that use case. And then we'll actually implement the pipeline in a way that kind of helps solve those challenges. Sound good? All right, so I was looking around last week and I found this like really interesting new data set that no one's seen before. It's called the iris data set. And if you haven't seen this, because it is pretty new, basically what this data set includes is a bunch of attributes of iris flowers. So they're like measurements of the flowers. I don't even know what units they're in, I don't know. And a corresponding species of those flowers. So basically the idea with this data set is you have these numbers and you're trying to predict the species of the flower based on this set of numbers about the flower or measurements about the flower. So the way that we might implement this workflow, if we were to do it in kind of a more real world scenario, is it wouldn't just be a single stage workflow. What we would want to do is have one program, which is actually the program that I just showed you, this train.jl, that takes in this data set and trains a model and then outputs a persisted version of the model. The reason why we'd want to do that is if we're actually putting this into some sort of environment where we want to use it, we don't want to retrain our model every time every time we're trying to predict something. At least often that's the case. So we want to do the training, represent the model, and then utilize that model over time. The next thing that we're going to do is we're going to have infer that takes in that model and then takes in new sets of these attributes each in a different file, or one file with a bunch of attributes, and then makes the corresponding prediction of the species of the flower. Okay? And it utilizes that persisted model to do that. Does that seem reasonable? Yeah? Yeah.
Is this going on in the Docker image or using the Docker image?
So great question. So the question was, is this using the Docker image? So here, I've kind of represented it as like, you're on your laptop, this is what you produce to solve this problem. Now if we're thinking about actually doing what we want to do, integrating it into some other environment, into some other infrastructure, a natural next step, like you said, would be to take those programs that I have written, I know work, and put them into a couple of Docker images that do the training and do the inference. And you could Dockerize these things and then still test them locally, if you have Docker running, and see that they work locally. Yeah, what was the question?
Why not do the development in a Docker image?
Yeah, I think that's some people like to do that, some people don't. I think that's mostly a preference thing. I would say that the important piece, so that, the question for the video was, why wouldn't you just do the development in the Docker image? I think that's a good way to do it. Some people find that a little bit awkward. But I would say the one thing that you do want to do is build your Docker image, and before you're like, oh, now I have my thing in a Docker image, I'm going to put it on AWS or put it on my cluster or whatever. You want to actually run that image on Docker on your local environment to see that it behaves in the way that you would expect before you actually deploy it to another place. Because as soon as you know that it runs a certain way on your Docker, on your machine, you have confidence that it's going to run the same way when you run it on Docker on a different machine. So I think that's the important piece. Some people do, have their complete dev environment in Docker. Yeah.
What are important performance considerations of any when using Docker?
Yeah. So there's certain. The question was if there's performance considerations when using Docker. So you, remember that like your Docker image is sharing the underlying resources of the kernel that it's running on. So you can definitely do like, if you're able to run something parallel on a certain type of node, you can definitely do that within your Docker image. But you also have to realize if you're running other Docker images on that machine, they're going to be potentially competing for resources. So there's that consideration. There's also the consideration that like, when you go onto a machine and you say Docker run, if the image isn't there, it's going to have to pull it. So it's not going to run instantly. As soon as you pull the image, it will pretty much spin up, not instantly, but there will be some associated like spin up time, which is minimal if you're not pulling it. But there is that time. So like that, I guess, is a consideration. There's also certain like network considerations, like if you're mapping certain ports or reaching out to an API or doing that sort of thing, you have to deal with all of those things. I would say, for most of our users, that isn't a blocker for them. But I know that there's people on the internet that talk about like certain performance things with Docker that are probably above my head. So I would recommend looking at that. But yeah, I would say those are kind of the three different things that I know people kind of struggle with a little bit. So yeah, other questions? Okay, so we have our workflow. We like our workflow. We've Dockerized our Julia. So now we have not only one Docker image, but we have a couple of them. And you can imagine, this is a pretty simple workflow. You can imagine that there would be, in a real world case, there would be other of these Docker images that you would be wanting to use. So now the question comes like, well, what do I do? Do I like go onto a machine and spin up each of these individually? Do I, what if one goes down? How do I monitor it? If I'm deploying these on different machines, do I have to like spin them up and then take care of like network stuff? And then like there's just a bunch of concerns around like if you have a bunch of Docker containers, how do you actually manage and deploy those? So this is really like Docker exploded, over the past few years, and then people started having this issue like, now we have 1,000 Docker images. How do we deal with that? So this is really like why in recent times people have really started talking about orchestration and scheduling of containers. And so in order to solve this problem, this is where we're going to introduce Kubernetes. So Kubernetes is another open source project that came out of Google. There's various different schedulers and orchestration tools to handle this sort of thing. I think far and above, like Kubernetes is like taking pretty much all of like most of the market share in that area. So I think it's a good one to look at. There's certainly other ones that do other things, but Kubernetes is, I'd say, the fullest featured of them, and has proven to be pretty good. It runs certain things like Pokemon Go is all run on Kubernetes and that sort of thing. But yeah, basically it kind of addresses this issue. I have all of these different containers. I want to schedule and run them on a cluster of machines. Kubernetes, you figure out how to do that. I'm going to tell you what to do, and you're going to figure out how to do it. So it's like a declarative thing. You can say like, I want 7 instances of this container, and if you have like 50 nodes, it's going to schedule them such that the resources are spread out nicely across the cluster. And if a node goes down, then it spins up another instance on another node. It's like self-healing, and you can do auto-scaling and like all of this incredibly magical wizardry that comes with Kubernetes. So that's kind of the tool that we're going to use. And again, kind of mapping back what we're trying to do to these goals. We want to have autonomy. So again, Kubernetes works with containers, so you can deploy any of your containers, whatever they are. And in terms of compatibility, this is an open source project. You can deploy it anywhere, some places with more struggle than others. But I mean, you can obviously deploy it in the cloud environments. You can deploy it on-prem. You can deploy it on OpenStack. You can deploy it on Raspberry Pis. Okay, so it's pretty flexible in that regard, and like I said, has quite a bit of adoption. Okay, questions about that piece? Yeah.
Do you find it scales well to starting a large number of nodes?
Yes. So the question was. Yeah.
My impression was it's more about making sure you have a set of infrastructure which is like more long-running servers rather than short jobs.
Yeah. So the question was kind of twofold. If it's actually intended to scale up to very, very large clusters, and also his impression was that it was meant to be kind of for a long-running cluster where you would have maybe web services up and that sort of thing. So in the first case, like I said, I think at the last, I don't know what the last number was, but there's people certainly running like thousands of nodes, Kubernetes clusters in production, including like the Pokemon Go one was a big one, but there's many, many other cases. And there's even Kubernetes federated now, which will let you spin up your workloads across different regions. So if you're like, I want to run this in Asia and this, and all of that is kind of, so it's meant to handle that sort of thing. In terms of the long-running clusters, I would say that a lot of people are using it out there for that. But what I'll be showing today, all of the actual data that our workflows depend on is not stored like on the Kubernetes nodes, which means that you could spin up a 1,000-node Kubernetes cluster, do the processing on your data, have it be stored and be versioned, and then take down your cluster, and then a month from now when you want to rerun it, spin up the cluster again. The only piece that would need to be persisted is that actual data that you're likely already persisting. Yeah. Other questions? And that kind of comes out of like the container world too, because all of this is built on, it's built on Go, so it's very lightweight. It spins up very quickly, and also like the containers and the pods and Kubernetes are meant to spin up, as instantly as possible. So all of that's kind of built in.
Yeah, it's interesting. So I don't have personal experience with this, but some guys at my work were trying out Kubernetes for like nodes or something
Yeah.
like this. And we found, I think what they found was, and this was like 6 months or a year ago,
Yeah.
that it had trouble with like, here's 10,000 things, run them all, I'll stop them in 1 minute or something.
Yeah.
Finish the job.
Yeah. So
Improved by then.
yeah, I think it's constantly improving. I think at least like 6 months to a year ago, I think the official like we approved Kubernetes for use with I think it was at like 5,000 nodes. I think since then they've gone up. I don't know what the official number is now, but that's kind of something that is progressing over time for sure.
Worth looking at again.
Yeah, definitely. Other questions, thoughts? Yeah.
If you have a large sort of data set, what's the way of distributing that data set amongst your Julia cluster?
Yeah, so great question. So the question was, if you have a very large data set, what is the way of distributing that data set across the cluster? So that's a great question that's not solved by Kubernetes itself, but we'll get into that actually next. So that was a great question to lead into, well, not next, but close to next. So let me know if I don't answer your question. Yeah. So we have Kubernetes, but there's a couple of things that we're not dealing with yet. So we've learned how to Kubernetes is going to help us schedule all these containers and this multi-stage thing. But for one, as was just mentioned, how do we actually deal with the data layer on this? How do we distribute the data to the different pieces of our pipeline? And then also, how do we actually accomplish these goals that aren't really addressed yet in terms of provenance and reproducibility? Because we're going to spin up these pods in Kubernetes maybe, which pods just means like a container running in Kubernetes. So we're going to spin up these containers. They're multi-stage. How do we actually connect those? And how do we track like what's flowing into what and what's been processed by what and what went into what where? All of that isn't really addressed by Kubernetes itself. And that's kind of why we built PACHYDERM, or at least part of the reason why we built PACHYDERM. So PACHYDERM is a project that I work on. It's another open source project. It's an open source project for doing data pipelining, containerized data pipelining, and data versioning. So there's like these two really kind of central features of PACHYDERM. And these really help us deal with the problems that I just mentioned and the challenges. So in order to kind of describe how that works, I think we can just use the use case that we've been talking about. But what I'll emphasize in this is that we have reproducibility because PACHYDERM provides data versioning. So kind of think of like Git for data. We're going to be actually version controlling our input and output data for every stage. It provides provenance because we have that versioning also combined with this multi-stage workflow, which I'll describe in a second. Again, we're autonomous because we can run, it's all containerized, so we can run whatever tools or frameworks we want. And it is compatible with Kubernetes, which again is kind of like experiencing this general adoption and at least fits in with many different scenarios. So in terms of the workflow that we're talking about, let me just describe kind of how that would run down. And then this is what we're all going to deploy together. So we'll go ahead and get hands-on with that. How are we doing on time? Oh, OK. Oh, we're golden. All right. So this is kind of how the same thing that I showed before would look in PACHYDERM. Well, not really look. I mean, this is an artist representation, if I want to consider myself that. But again, we have these same Docker images, right? So we have, these were kind of the same ones that I showed before and the same created by the same Docker file that I showed before. What's different here is I've kind of represented each place where we have data in our workflow with the cylinder. And what I'm representing by that is that each of these places where there's data, where there's a collection of data, that is a version set of data, what we call a data repository. Similar to like in GitHub, you have repositories of code, right? This is a repository of data, a version collection of data. And so where we have our training data, if we make changes to that over time, we can go back and see what was the state of my training data at any particular point in time, what was the state of my model at any particular point in time, et cetera, et cetera. And then if we add in the pipelining piece to this, where now we're saying, I'm going to create a data pipeline where the input and output is each one of these version collections of data, then some really interesting behavior pops out of that. First of all, it gives us this idea of provenance. It says, like, this version inference came exactly from this version of my model, which was produced from exactly this training data set, which came exactly from this raw data, blah, 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 all the way back in the whole lineage of things. It also gives us a way to deal with like this debugging and maintenance issue, because if we're versioning things over time, maybe we commit like corrupted data or something like that, we can always revert to the previous versions and update our pipeline. And then finally, it gives us some things that I won't emphasize a lot here, but there's some actually pretty interesting processing, unique processing capabilities that come out of this in terms of incrementality. So like if you're aware of what data has changed, and let's say that you've already processed like 1 million of these attribute files, and you add like one more, if you're aware of what data has changed, you only need to process that new data in many cases, not all the other data. So PACHYDERM is kind of smart in this diff awareness and giving like the actual diff of the data to containers if that's what you want. In terms of the question that was asked before about how this data gets into the processing stages on our cluster, all of this data, that's shown is backed by an object store. So that could be like S3 or GCS or a cloud offering, or it could be any other one. It could be like one that you run in OpenStack. It could be Minio, it could be Ceph, Swift, any of these just kind of like generic object stores. And that's where the data lives. And then when we actually do our processing, when these containers come up on Kubernetes and we're about to do our processing, PACHYDERM has built-in functionality to look at what data hasn't been processed and then shim that data into those containers that are running. So as I'll show in a minute, basically PACHYDERM is an application that's running in your cluster. And when you say, you know, create this model pipeline stage and process my training data, it says, as soon as there's new data in training, it says, this data in training hasn't been processed yet. I'm going to shim that into my running model container. It's going to be processed and then output. So it's kind of this shimming functionality. But the interface is very similar. So like you don't, like before when I showed the train.jl, there was no like using PACHYDERM or something. It was just an interface to the local file system. So that Julia program, it just read local files and it wrote local files. And so when this container comes up, PACHYDERM shims in that data to where all you have to do is read that from local, like you would from local files, and then write out files. And PACHYDERM is smart enough to kind of version that on the input and the output. So instead of just reading and writing normal files, you're reading and writing these versioned data sets. Yeah?
Do PACHYDERM's repositories generally have a philosophy of multi-repo versus mono-repo, or do you handle both?
Yeah, I would say that so the question was around like whether we have a philosophy around mono repos or multi-repos, or how like we suggest things. Generally, how we've kind of developed our best practices is around something similar to this, where like if a set of data has a different function or meaning, then it's put into a different repo. So like training data is different than the data that we're actually running through to do the inferences. So you could definitely put those in the same repo and functionally it would work. But generally what we've seen kind of make most sense to people is that they separate it out. But you could definitely put it in the same repo, and you can actually give, so like if you had those in the same repos under different directories, like training and attributes, you could have just the training directory be input to one phase and the attributes be input to another without mounting all of the repo. So that's definitely possible. It's kind of preference, but the one thing would be that each stage that you create has a corresponding output repo. So that is definitely, I guess it's forced on you. That way, every single pipeline has a very natural and very quick to access output repo that corresponds very closely to that processing. Yeah?
Okay, and just so it's clear in my mind, PACHYDERM's repos are just for data. You keep code in separate repos?
Yeah, so that's a great question. So the question was if these repos were just for data or also for code. So we version any files, so technically you could version code. That's not the best practice. So you would version your code in GitHub or whatever version control you use. And what's really versioned here code-wise is the containers or the images. So in a typical scenario, you would make an update to your code in GitHub. Then you would build a new Docker image with that new code with a specific tag that corresponds to that version of your code, maybe the commit ID or something like that. And then you would update your image in PACHYDERM. And in this way, you have kind of a version history of which images you were using, along with that mapping back to the specific code version. That's kind of the best practice. If you try hard enough, you can definitely shoot yourself in the foot here. If you always overwrite your images, obviously we're not going to have a record of that because we just have a record of the one. But we also provide some tooling that kind of helps with that. But yeah, that's the thing. We're kind of versioning these containers, which are a representation of your code, along with the data that they're processing. Yeah.
So then I have to manage the correspondence between the tags and the build recipe.
So you can, if you want, manually, but we also have an automated way of doing that. So I'll show you in a second. You can update pipelines, and there's a flag in there that will automatically do all this retagging and mapping for you. So if you don't want to keep that manual record, then you don't have to. So that's something that's kind of extra sugar. Yeah. Yeah.
So I'm thinking along the lines of tagging specific image versions with data output versions. What do you feel like are the biggest uses for that? Is it just the reproducibility, so we can go back and see where things go from, or is there more to that where I can not necessarily migrate old repos to new ones, but deprecate old data repositories like that? Sure,
yeah. So there's a bunch of different use cases here. I would say the one I'm kind of emphasizing is this reproducibility provenance case, which is very important in a lot of scenarios. Certain users don't care about that though. Certain users might want this kind of change data processing element where you're processing off of the diffs of your data, which is actually very different than the use case with typical big data software where you might have to batch process everything again to ensure that you're up to date because you don't know what was new data and what wasn't data. So we have users that have that use case, and then finally we have users that are kind of maybe in neither one of those scenarios, but I would say are experiencing these workflow issues that I mentioned around we have all these multi-stage things, we're working on a team, basically it's the Wild West and everybody's doing everything, nothing's being tracked, we don't know how to put things into production or tie things together. So there's definitely those users. But you can do things similar to what you said. We have users that don't want to, so they might want to deprecate data or they might want to split off data. You can definitely copy from one repository to another or create new repositories where you might deprecate one repository and push the data to another repository, or even we have this branching idea where if you have different versions of your pipelines or different teams that are working on different pipelines, you can kind of branch as well. So there's a lot of possibilities. I would say the majority, though, are kind of around this workflow, reproducibility, provenance, along with change data processing. Yeah. Other questions before we get our hands dirty? All right, let's do it. So what we're going to do is we are going to deploy all of this each of you have your own cluster, your own machine, and we're going to kind of walk through this deployment and then see some of these features as we go along. Again, the repo README, so now we're talking about the GitHub repo that I created. That README has all of the commands that I'm about to do in it. So if you get lost or you don't remember, always you can refer back to there. And if you kind of miss one or something gets messed up or your machine catches fire or whatever like that, look at your neighbor, kind of collaborate. I don't know if I'll be able to get to all the questions until the end to get through everything, but then I can always spin up another one of these instances for you to try like the rest of today, or we can sit down together and do it, and you also can do the same thing with the local installation. So all of that to say, don't worry if you don't get every single piece of what we're about to do. All right, so we have this pipeline. The first thing that we're just going to kind of note here on our cluster, let me go back here. So if you run, so kube control is the CLI tool for Kubernetes. Remember, we're going to use Kubernetes to schedule all of these containers. Kube control is how you interact with Kubernetes, at least one way. There's APIs and there's clients and all of those things. And we're not really going to use kube control too much, or kubectl or kubectl or however you want to say it. But just to note, if you do kube control get all, it will show you that this is kind of what the Kubernetes cluster looks like. There's a couple of pods running. Again, pods just mean these containers that are running in Kubernetes. You can see that we have a couple running. One of them is PACD, which is our PACHYDERM daemon. So in other words, we have PACHYDERM running on this Kubernetes cluster. So the PACHYDERM, quote unquote, that we're going to be talking to is just this lightweight service that's running on our cluster. That's what we're going to be talking to back and forth to do the following things. And you can confirm that PACHYDERM is running by just using our command line tool, which mimics the same form, pack control. Again, there's multiple ways that you can interact with PACHYDERM. There's not a Julia package yet, hint, hint, contributors. But there is like a Python client, and there's a UI that provides some visibility. It's all based on gRPC and protobufs, so you should be able to create a Julia package. So someone can PR that as well this week. But you can confirm that PACHYDERM's running by just doing pack control version. Should show you something like this. If it's the first time you're running it, it might give you another thing that says, I created a config for you. But that way we can kind of see that PACHYDERM's running. OK, so we have Kubernetes running. So your instance is connected to a Kubernetes cluster. PACHYDERM is running on that Kubernetes cluster. We're able to connect to Kubernetes. We're able to connect to PACHYDERM. Now let's actually kind of figure out how we actually build and deploy out this pipeline. The first thing that we need to think about is that we have two collections of data over here on the left that are kind of our inputs for our pipeline. They're driving everything else. We have our training data, and then we have these attributes that are input to our inference. So the first thing that we need to do is create those inputs for our pipeline. And again, the input, any input-output data is a data repository in PACHYDERM. So currently, we can see that if we do pack control list-repo, you should see something like this. It just means that we don't have any data repos yet, right? We don't have any of these version collections of data on our cluster because we haven't created any yet. So to create those input ones, we can just do create repo training, and then create repo attributes. Then if you do the same thing, list repo, you'll see that now we have two data repositories with nothing in them. created a couple seconds ago. We have this version collection of data called training and a version collection of data called attributes. Does that work for everybody? Yeah? Okay, so that's not that exciting. I mean, if you're interested under the hood, basically we just made a record that says, I have these version collections of data. We haven't really done anything yet. So let's go ahead and put some data into our training repository. So if you go to the workshop directory, and then if you go to data, you'll see that here we have this really exciting data set. This is just the same one that a lot of you guys are probably familiar with. Again, columns of numerical values paired with a species of these flowers in CSV format. And from this directory, what we're going to do is we're going to do pack control put file into our training data repository on the master branch. So again, think kind of like get-like semantics. We're committing this file into the master branch. And we're going to give a couple of flags, so -c and -f. -c just means like there's another way to do this, which is you can open a commit and then stream a bunch of data in and then close the commit such that all that data goes in one commit. Here we're just doing that all at once. We're saying open the commit, put the data, close the commit so I don't have to execute 3 different commands. The -f just means that we're putting in a file. There's a bunch of different ways to put in data in PACHYDERM. You could give it a URL, you could give it a list of files, you could give it an S3 bucket, you could copy from another data repository. Here we're just saying put this file, irish.csv. So again, it's pack control, put file, training, master, -c, -f, iris. Okay. Now to confirm that worked, you can list repo again, and you should see now that in our training repo, we actually have data. And if we look what data is there, you can do list file on training master. If I, I think I need a space. There we go. Then it will show you that iris file, which is the only thing we put in. Everyone good? Questions? So it's important to note here, like, it kind of seemed like I did everything locally, but I actually pushed that file to the cluster. It's living in that object store that I mentioned. And when I pushed it in, PACHYDERM made a content addressed hash for that file. That is how it's going to manage the version control for this data set. So actually quite a bit went on under the hood when we did that. Now let's go back here, and the next thing we want to do is we have now these repos. We want to create this first stage, the model training stage. Again, we're going to use that same Docker image that we showed before. We just need to tell PACHYDERM how to run it and what the input is. So the way that we do that is with a JSON specification. So if you look under the root of that repo, the Julia workshop repo, there's a train.json file. If you look at that, there's a few things in here, and it might look complicated, but let me kind of describe what's going on here. There's just kind of a few different pieces. We're saying, this is kind of like declarative. We're saying PACHYDERM, create a pipeline stage called model. And for that pipeline stage, use this Docker image, which we built before. And when you run that Docker image, run this command. So this gets at the question, I forget who it was before, why we didn't put a command in the Docker image. As of now, like this is the way that this is done, mainly because like we have this spec. You might have the same Docker image that you want to run different commands in for different stages of your pipeline. And also we have to do this like shimming of data operation. So just because of all of those technical things, the command is specified here. And it also makes it pretty easy because we can change what command is executed. Yeah?
Where did the PFS training path come from?
Yeah, so that's the next thing. So the question was about this PFS path. So here, again, like we're saying, create this pipeline model, use this Docker image, execute this command, and run that on this repo training, okay, on this repo here. Now, the reason why I'm doing these paths, so you would run this program very similarly if you were running it locally. You would just specify the path of where your Iris CSV is and where you're going to output your model file. Here, the only thing you have to change when you're running it in PACHYDERM is you have to tell that program where that version data is that you're going to be processing. When this container comes up, what PACHYDERM is going to do is it's going to shim in the data at a special directory /pfs / the name of the input. So here I've said my input is training. So it's going to put that training data under /pfs / training Iris. And that's where I can have access to that version data. And then whatever I write to this kind of magical directory /pfs / out, PACHYDERM is going to version on the output. So you could have multiple inputs and all of that, but this is kind of the convention that these things are going to show up under /pfs / name of the input repo, and then whatever you're outputting can go to /pfs / out. I think you were next, yeah.
Yeah, could you just define exactly what you mean by shim?
Yeah, so PACHYDERM creates like a mount when your container comes up and basically pipes in the data that needs to be there for you to access it. There's a couple different ways that this works. It might go ahead and copy over that data into the container, but that's not always like great because, especially if you have very large scale data. The other way that this is done is like a pipe is created and you can do it lazily. So like if you have millions and millions of files, you don't want to mount them all. So in that way, like your data is mounted as you read it. So you might only read like 1% of that data at a time. Yeah. So yeah, I think there were a couple more. Yeah.
We did create a PACHYDERM thing called training, but we didn't create one for the output. So is that one?
True. Yeah. So whenever you spin up a pipeline, PACHYDERM automatically creates another data repository for the output of that pipeline, which will be named the same name as this name, model. So you'll see that when we spin it up, and that will be where the output goes. This way you can always specify /out. You don't have to worry about the naming. It just goes to that repo. Yeah. And there was a question? Okay, yeah.
Can you help us understand maybe a little bit under the hood the concept of the repo?
Sure.
Is that something that lives like in Kubernetes? There's a PACHYDERM service. Is that the repos live in the PACHYDERM service that's running? Is it creating separate pods for each repo?
Yeah, so that's a great question. So the question was what is a repo in essence, and where does it live? So if you notice that, let me go back here so I don't wrap as bad. There's actually, in my Kubernetes cluster, I'm running PACHYDERM. The other thing I'm running is this etcd, which also runs in Kubernetes anyway, but we utilize it as well. So this is like a distributed key value store. And so what actually happens, like when I initially created those repos, what happened was I just created a key and a value in that store that said, I have these repos. Okay? Now what happens over time as you actually put data in and out, I mentioned that those hashes are created, then those hashes are indexed to those various repos and the various jobs that are run. So we basically maintain this index or metadata store that manages all of those semantics. So it's really just keys and values in this store. Now in terms of like where that lives, there's a piece of that that's cached on the node just for like performance reasons, but all of the things associated with your data actually live in the object store. So like you can very easily take down this cluster and bring it back up and start with the same repos, the same history, all of that. So this gets to the question that was brought up earlier, like what if I'm doing like a batch job on 1,000 nodes and then like I want to shut everything down and bring it up next month. All you would need is to have that data stored somewhere in the object store, and you could bring that back up. Yeah.
Is it like snapshotting
So no, it's so when the data comes in, it like for each file, it's content addressed, and that creates a hash. And so that hash is what is associated with the various repos. That way, when like your data changes, it corresponds to a new hash, and so that is then how like the different repos and that sort of thing are managed, which also helps us deal with space efficiencies, which aren't really dealt with well in Git. So like if you write, you know, 1 million files and then you write another 1 million files where there's like a 50% overlap, we won't duplicate all of those files because it's the same data. We just like add the new data. Yeah. And you can like reshuffle and bucket things and it won't duplicate. Yeah. Yeah.
So what if parts of a file are modified? Do you rewrite the whole file again?
Yeah, so that's a great question. So the question was, what if parts of the file are modified? Will that just write a new file? So the short answer is yes. We do things at the file level also to be agnostic to file formats. So as was mentioned, like sometimes you don't have a choice of what formatting you're using, and we didn't want to get into a situation where we're like, we support CSV and we support Parquet, but not your thing, so sorry. But that also, like if you have a file with very many records, what you can do to kind of like make this a little bit more convenient if you want to version per record is we have a splitting functionality where like you can split your file, or I should rather say PACHYDERM will split your file under the hood, like record per file, and it will version per record. So if you're wanting to have that versioning, you can, at least for some common file formats. Yeah.
And is there some kind of replication for high availability?
Yeah, so there's one node. The question was about high availability and replication. So I've shown one instance here of PACD and etcd. Those you can have replicas of, and those will have all of the nice Kubernetes things of being rescheduled and auto-scaling and all of those. And as well, like your individual stages of your pipeline. I'll illustrate in a little bit, but you can create replicas of those to process in parallel, which also gets to your question about data sharding. And all of those will be rescheduled and highly available. We kind of let Kubernetes handle that under the hood, which it does very well. Yeah. Yeah.
So I've got a couple of petabytes of data. What happens if I chucked it in here? Does it duplicate it at all? Like,
so it depends how, the question was like, what if I have petabytes of data? Will it all be duplicated in that? It definitely depends on the format and how that's split up. So like if you have petabytes of data where there's like millions of files, and then like you put in more data where there's a lot of overlap in the data, I mean, there won't be duplication of the data that's not different. But for the data that's different, like if there's 1% data change or something, that will be what's added. But we do have to maintain those different versions of the data at some level, the ones that's changed.
so there's very much a model of you guarantee that the data set will be there when you go back to look at it later.
Yes, definitely.
Of course.
Yeah, definitely. And we
You can't afford to pay for that.
Yeah, definitely. And we do have certain users where they use this for their pipelining and scheduling, and also like this change data processing. But also for like certain web users, they literally do not want their data saved for various privacy reasons and all of that. So they kind of follow this deprecation sort of workflow that was mentioned earlier, where they'll clear stuff out, but they'll still be working on all of this triggering and containerized pipelines. It's just that part is not important to them. Yeah. Other questions? Yeah.
Can you attach like custom metadata to the files you commit?
Oh yeah, definitely. So the question was around, can you attach custom metadata? So we're completely agnostic to what you put in these repos. So you can put metadata, you can put Parquet files, you can put like Giphy kittens, you can put like whatever you want, and all of those things will be version. And in another example, I don't think it's in this one, but I did store some metadata with the model. So that's one way like you could do that, because in this case, it's not human readable. But you can definitely, it's whatever data you want to put in there. Yeah. Other questions? All right. So let's go ahead and build up the rest of this pipeline, and then we'll do some extra fun things, hopefully. So we've got this top piece. Our model is trained. Now let's build out this bottom piece, the inference. For sake of time, I won't show you the inference file, but it's under infer. It's just another program here. And I then have this, I have this other JSON that specifies my inference stage, the respective container, the command. The big difference here is that I have two inputs. I have the model input and the attributes. I don't just have the one input. But let's go ahead and create that. So we can do pack control create pipeline infer.json. Oops. What did I do? Model not found. Oh, did I got ahead of myself. Did we not? We didn't ever create the model pipeline, right? Okay, yeah, PACHYDERM saved the day on that one. Okay, so stepping back for a moment, I forgot we got into all the stuff. Let's actually create the model pipeline first. That first stage. So just do the same, but with model.json.
You mean train.json?
Train, thank you. Man, I am all off. Good thing you guys are on it. So immediately when you do that, you'll notice something happens. If you do list job right after you create that pipeline, you'll see that PACHYDERM has automatically spun up a job to do that model training. So let's think about like why that happened for a second. Why that happened is that we had this repo called training, and we put data into it. Data that hadn't been processed yet. And PACHYDERM was aware this data has been added to training. Well, then we created a pipeline that is supposed to process that training data. And PACHYDERM said, oh, you've told me to create this pipeline, but there's data that hasn't been processed yet. So I'm going to go ahead and spin up a job to do that processing and output. So this should take a minute or so because you have to pull the Docker image in. It'll go a little bit quicker next time. But eventually you'll see this success, hopefully. Fingers crossed, all networking things and all goodness. But that will eventually get done. And then after that, if you do list repo, you'll actually see that, as was mentioned before, there was a repo that was automatically created to version the output of that model pipeline. If I do list file on that model repo on the master branch, I'll see that there's my model file that was output from my Julia program that's now versioned in this repo. Okay, does that make sense? All right, so the next thing we can do is what I tried to do. Let's go ahead and create that inference pipeline. So again, just referring to that different specification, infer.json. Now it actually works. So you'll notice that if the repo doesn't exist, it won't create the pipeline, which is probably a good thing. Now, if I list job after that, I'll notice something kind of interesting. It didn't spin up a job this time when I created this pipeline. So why is that? Yeah, actually, there's no data to be like we created the repo, right? But we actually haven't made any modification to that repo that would necessitate processing at this point. We need to add data into that repo. So in order to do that, you can go to data again, and then go all the way to test. So actually go to this repo. Here you can see that there's a couple of input files that look like this, just with a bunch of attributes, no species. Okay. And we're going to put those into attributes. So if we do put file attributes master-c-r-f, this is the same as before, except I'm putting both of these at the same time. So I'm doing it recursively for this repo, or for this directory, putting all the files from this directory. You can put file attributes master. When I do that, I'll notice that, okay, now PACHYDERM has spun up this job to do my inference, because now I put in data that needed to be processed, and it automatically spun up that thing. So this is, again, like getting back to like, we're knitting all of these things together such that it's very well defined what goes into what and what's updated when. And PACHYDERM is automatically taking care of all of that triggering and using Kubernetes under the hood to spin up the respective containers. So those are kind of the various things that are at play here. Again, this might take a second with pulling the Docker image, but that should work here. Let's see. OK, so mine succeeded. Again, I can help you debug after or something like that. But if you list repo now, you'll see that there's a new repo called inference, right? Again, a repo was created to version the output of that stage. If I list file on that repo, I'll see that there's 2 output files corresponding to each of my 2 input files. And if I want to look at what those results look like, I can get them one at a time with get files. So pat control get file, and we'll just do like 2. So if I do pat control get file inference master 2.csv, I can see that here's my inferred species for each one of those attributes that I put in. So we have version data, input and output of each stage of this multi-stage pipeline that's stored in an object store. We have multiple Docker containers being scheduled on a production cluster, Kubernetes cluster. And we've strung things together with PACHYDERM in this way to where the data is actually going to the right containers. And we've kind of maintained this record of what's going into what where. There's a few other, so there's like some bonus exercises down there, and I want to show you a couple of them before we end. But this was like the main meat here. Hopefully, a lot of you guys got that working. Are there any questions before I just show a couple other things? Yeah.
About the provenance of data. If I ran this a couple times, updated my model, reran, etc., how can I ask for an old output and who generated that old output?
Yeah, great question. So the question was, this is all good and fine. I've done one run, but really this like idea of reproducibility and provenance is really important when I'm updating things, when I'm changing things, when I'm rerunning things. So let's actually go ahead and mimic that, which this is included in one of those bonus exercises if you get time to do it. But if I go here to train, I actually created 2 Docker images. You might see this in the repo, but I created a decision tree model. And then there's one that trains a random forest. I just tagged them differently. So I'm going to go ahead and update my model to this different model, which again is mimicking this kind of update of code and update to a new Docker image. So when I do that, I can then run update pipeline for the model. And if I'm quick enough, if I look at what's happening here, sorry for the wrapping. What happened is that PACHYDERM said, you've told me there's a new model. I now know that the results in the model directory are not up to date. So I'm going to rerun my model training with your new model and generate a new persisted model. So that's what this first one that's running is doing. Now there's various ways that you can configure that as well, because you don't always want to update your historical data. Sometimes you just want to process new data. That's fine, you can do that. This is just kind of the default. Again, it's pulling the image here. This should finish in just a second, depending on why. What now? Great question. So, which was just answered. So what happened is it updated this model right here, right? And then PACHYDERM knew that there was new data, there was an update in my model directory, and that my inferences weren't up to date with that latest model. So it actually automatically ran that inference again to success. And this is, again, the default behavior. It's like a pipeline that keeps in sync with all your latest changes in data and code. Again, that's all configurable as well. But getting to your point, part of the magic here is that if I look at these jobs, I've now run 2 inferences. I've run this one and I've run this one. So how am I to say which model or which training data was used for each of those? So this is where this idea of provenance comes in. So if I go to this first inference and I inspect that commit on inference right there, it will give me that exact provenance for the exact model, version of my model that was used, the exact attributes, and the exact training data that was used to produce that exact result. And of course, you can go back and grab these commits and get your exact model from there and rerun it. You can go back to your data and pull that data to work off of locally, all of those good things. So this is kind of how that provenance comes out, and all of that's tracked automatically. Yeah.
Just a clarification question. The model there refers to both the model of JLD output and also the Docker image.
Yeah, so great question. So the question was, what do these correspond to? Do they correspond to like my pipeline or my actual data? So this commit ID right here actually corresponds to your data. So if you did like list file on model for this commit, it would show you that specific model that corresponds to that version. But I can see that that model, which is this model right here, was created by this job, right? So I can say pack control inspect job and give it that, and it will show me the exact job that was run. It turns out that was the random forest model, right? And I ran this command, and it resulted in, or it processed this commit of data on its input, et cetera, et cetera. So all of these things are trackable, and most of the time, I mean, it's nice to do this with the command line like we're doing. There is a UI that helps you get visibility into it, and you can also do this programmatically. So if you're like, you can spin up a notebook and pull all these different versions and analyze them, et cetera. Yeah?
So what if your model for some reason crashes halfway through? What happens to the data?
Yeah, so what happens is like you'll get a failed job, and there won't be an output commit with that. So it will stop the DAG at that point. But then you can also conversely, like if you process things up to a certain point it failed, and then you correct that, like at that point, it will only run the things necessary to like update the output. So you don't have to like rerun everything. If you just correct the one thing, like if your code was wrong and you update your code, it would just run that and what depends on it, not the things before. Yeah.
So talking of not running the wrong things, I just created a third CSV file and put it into the job, and it seems to say that it's run 3 jobs, so like it reran 1 and 2 again.
So you put a third CSV in.
Yeah, I just copied the second one in.
Okay, yeah. What probably happened is, did you do the update pipeline before?
No, I just added in a new.
Okay, I'll have to take a look. What should have happened is it should have spun up. Let's see. Oh, sorry. Let's see.
So I just oops. So where is it? Yeah. So I put in a file here.
Yeah.
3.csv, and then it started running. It started here and it was running.
Yeah, I'll have to look. What likely happened is there were 2 commits at some point. So like I said, what the default behavior is that when you make an update, it will update your corresponding results for each corresponding state of your pipeline. So like if you have 2 models that depended on that particular input, it will update that. So that's configurable. So I'm not sure exactly. I'll have to take a look what happened there. But it should, like if I do something like here. So for example, if I go in here and I delete a couple of these lines, and then, oh, that's probably start. Oh, sorry. Good call. So then I do start, commit, training, master. And then I'm just going to replace that file. Oops. And then I'll put it again. And then finish the commit. So that's just because I did a couple things in there. What should happen is the following. So if I look at now what's doing, it's rerunning my model, which was dependent on that one file. So it updated that repo, and then it spun up the model because it was dependent on it. But it didn't, like, it's just updating for like my current model. I'm not exactly sure what happened in yours. There's probably like a couple commits somewhere. So yeah.
Three hopefully quick questions. Did you say there's a REST API equivalent to the pack control?
Yeah, so the PACHYDERM's written in Go actually because it's built on Kubernetes. So there's a Go client, there's a Python client, there's a Scala client and R client being built, and I'm hopefully garnering support for a Julia client that someone will write here. But yeah, those are what's available now.
Okay. Access control?
Access control is a work in progress right now. We're building something internally to deal with that. There are definitely ways to integrate with the PACHYDERM client at the moment to handle access control, which is what our users are doing at the moment, but we don't have like a pre-baked solution internal. Some users are also kind of like siloing data in different branches or repos to like cut off certain teams. And you can do all that with the client as well. So.
Is there a mechanism to receive notification of PACHYDERM events as opposed to polling for state?
Yeah, definitely. So there's a whole logs section in monitoring, which will hopefully be added to the docs soon. But we expose both your logs of your applications that are running and PACHYDERM logs. So you can set up notifications based on like jobs running and all of those things, or based on like your own error tracking in your own code as well. So there's different ways to configure that, and we can integrate with like different tools like Prometheus or other things like that. So, yeah.
Can PACHYDERM use other orchestration tools like AWS?
Not currently. So currently, I mean, Kubernetes is the only one with the richest features that actually allow what we just did. If the goal was never to limit ourselves to Kubernetes, but I think the idea is like when those catch up, hopefully we can integrate them as well. But yeah, not at the moment. So let me just mention too, I didn't do it here. So there's also, if you look at the repo, there's a way, we didn't quite get into it, but down here under, or let me go to the, go here. There's a way to parallelize things in PACHYDERM and do data sharding across workers. So if you're interested in that sort of thing, you can run that bonus exercise. And then I kind of did these other two down here. But again, there's resources at the bottom of this repo for Docker and Kubernetes, and then some PACHYDERM resources. I also included those in the slides here at the end, and I included them as hyperlinks, so I'll go ahead and tweet out these slides right now. Okay, hopefully that goes through. Okay, so those are tweeted if you want to look at the slides, and there's various links here to other examples. We have a public Slack channel, but I'm also Whitenack on the JuliaCon Slack that was just put up. So DM me there, DM me on Twitter, connect to me. I have more cards up here if you want. We're an open source project, so like your feedback is incredibly important. If you want to contribute, that would be awesome. Or if you even just want to give feedback or you know, try things out, that's awesome. Definitely reach out to me anytime with just general questions about pipelining or those sorts of things. And like I say, I'm really excited to learn from you guys this week as well. There's a kind of related article that I posted there. But yeah, that's kind of what I had. I'm not sure. I know we have to prepare for the next one. I think maybe we have time for a few questions, though, if there's more. If not, I can definitely I'll stick around and kind of help people if there were issues with the demo. Questions, concerns? Yeah.
My question is in general about code version. So when you showed the example of updating your model, you change the whole code base and you basically put another model.
Yeah, like a flip-flop.
Much more frequent thing would be you actually commit some change in GitHub in your code and you want to actually rerun that model.
Yep.
And in this case, that goes through what?
So that process. Yeah, basically, whether you do it automatically or not, basically the process would be that you would have a code change and a new Docker image would be built. And then you would do a similar update where you would update. You can either do like the manual switch that I just showed, but if you don't want to do that, we have a like push images tag, which basically does this whole tagging thing for you. So if you update your code and then build your image, then you can do it with that flag, and it'll automatically update and retag and all of that stuff. Yeah. Other questions? All right, cool. Thanks, guys.